Good morning everyone. Today we will be discussing the accomplishments and history of Brahe and Kepler. These two scientists were known because of their contribution in astronomy in the science history. Before we start discussing, my name is Mark Abraham Hardin and my co-presenters are Sebastian Ayala, Stephen Corbito, Kelly Fajardo, and Yesha Precioso. Tycho Brahe is a Danish astronomer. He was born on December 14, 1546, and died on October 24, 1601. He was married in 1573 into a peasant's daughter named Christine. His parents are a noble Danish, Otto Brahe and Betty Bailey. At the age of 2, Tycho was abducted by his uncle and auntie because they have no children, but soon after his parents agreed for them to raise Tycho. Tycho was supposed to have a career in law, but after witnessing a solar eclipse, he began spending more time with mathematicians and science professors who taught him the art of celestial observations. By the time Tycho was sent to Germany by his uncle a few years later, he lost his interest in his law studies. Instead, he read astronomy books and starts improving his instrument. While in Germany, Tycho got into an argument with another student at a party over a mathematical formula, resulting into a sword fight and Tycho losing his nose, and also left a permanent scar on his forehead.
Let's proceed to Tycho Brahe's educational background. He studied law at the University of Copenhagen 1559 to 1562. Tycho's interest in astronomy began with the solar eclipse on August 21, 1560. In Copenhagen, the eclipse inspired Tycho and wanted to learn how he too could make predictions like astronomers had predicted exactly when it would happen. And at the age of 17, he made his first recorded observation. Since then, Brahe was the first great observational astronomer. He proved that comets were not objects within our atmosphere and that supernovae were not positioned between Earth and the Moon. Thus, we can say that he was the most skilled visual observer at that era, however, was not skilled theoretically. And did you know that he was kidnapped by his uncle and aunt? It happened when his parents were away from home. Because Tycho's uncle and aunt were childless, eventually, Tycho's real parents agreed to this. So Tycho was raised by his uncle and aunt as if he were their own son. And they sent him to the University of Leipzig, 1562 to 1565. After that, he traveled wildly throughout Europe, studying at Wittenberg, Rostock, Basel, and Augsburg in 1565 to 1570. On November 11, 1572, he suddenly saw a new star brighter than Venus, where no star was supposed to be, in the constellation of Cassiopeia. Tycho's discovery on the new star in Cassiopeia in 1572 and his publication of his observation of it in De Nova Stella in 1573 marked his transformation from a Danish dilettante to an astronomer with a European reputation. He carefully observed the new star and showed that it lay beyond the moon, and therefore was in the realm of the fixed stars, to the world at this phenomenon, a supernova, which could be seen by the unaided eye until March 1574. Lastly, he was the last significant observational astronomer to not use a telescope.
He became so well known as a scientist that the Danish king kept trying to give him castles so he wouldn't move away. But Tycho kept turning down castles until he got his own private research island, Ven. On Ven, Tycho built two structures, Uraniborg or the Castles of the Heavens and Stieneborg or the Castles of the Stars. Together, these castles represented the most state-of-the-art research labs of the day. Here, Tycho built a scientific empire. He had his own printing press, paper mill, alchemical equipment, and most importantly, huge expensive instruments and an army of staff scientists working for him. Tycho and his staff produced some of the most precise naked eye observation of the night sky ever. These were roughly twice as precise as similar observations by ancient Egyptian, Babylonian, and Greek astronomers. Tycho's observations were not surpassed by those made with telescopes for 100 years. Tycho believed in a geoheliocentric cosmos, that in this model, the sun orbits the Earth, but the other planets revolve around the sun. So Tycho was moving away from Aristotle and Ptolemy, and this hybrid model actually solved the bunch of the math problems astronomers were having with the Ptolemaic model. But it also placed the sun on a collision course with the planet, so it's not perfect. But even if the Tychonic model of the solar system had flaws, his observations paid off ways in other. Tycho observed and took other precise measurements of the same sky all the time. But after all that hard work, Tycho's life ended sadly. The old Danish king died and his 19-year-old son took over. This not so intellectual new king wanted his nobles to spend their energy on war, not science. So he roused up oppositions to Tycho's science castles, ripping up a mob to drive the patient observer into exile. Thus, Tycho moved to Prague in the Holy Roman Empire, where he died after only 2 years in exile, leaving behind an enormous, meticulously detailed catalog of observable stars and one very well trained assistant, Johannes Kepler. He was born in 1571 near Stuttgart, Germany. His grandfather was rich, but his dad hadn't done so well, dying as a mercenary in the Netherlands. Johannes went to school on a scholarship at the Latin school, seminary, and then the University of Tübingen. After college, Kepler taught math. Then in 1600, Kepler impressed Tycho so much that the older astronomer shared his secret datasets with him, and the two became close collaborators. Then politics happened. Kepler, a devout Lutheran, was told to convert to Catholicism or leave Prague, but Kepler, who used to call himself a mangy dog because he was so full of self-doubt, chose exile. When Tycho died in 1601, however, Kepler was immediately ordered to serve as the official imperial mathematician and continue Tycho's work.
Now, let's talk about Kepler's law of planetary motion. But before we actually go and discuss this with planetary laws, I want to give you a little bit of history. Before we talk about Kepler's, let's introduce a Greek mathematician scientist, Ptolemy. Basically, he had the view of the fact that the universe was centered around the Earth, and so we call this a geocentric view of the universe. Aristotle actually had a concept of a geocentric universe, but Ptolemy added some adjustment on Aristotle's view. So basically, the sun and the planets revolve around the Earth. That view held pretty much strongly for almost 1,500 years. Then came Nikolai Copernicus, and Copernicus published a book where he looked at the universe not as geocentric universe, but as a heliocentric universe. The heliocentric concept of the universe is now that the sun is the center of the universe and all other planets move around it. Along comes a Danish astronomer named Tycho Brahe. He made very accurate measurement and accurate charts of the position of the planets and position of the stars. We understand that Tycho Brahe's model view of the universe was still fairly geocentric, though he modified slightly to Copernicus' view. Tycho Brahe was very jealous of keeping those results and not wanting other astronomers to particularly use them. He later on employed Johannes Kepler, a German astronomer, but Johannes Kepler wasn't privy to all the data that Tycho Brahe actually had taken. Upon Tycho Brahe's death, Johannes Kepler had full access to the data, and that's where it actually come into Kepler's planetary laws of motion. So Johannes Kepler used the data that Tycho Brahe had collected to look at the understanding of the motion and understanding the motion of planets. And by careful mathematical analysis of the data, he came to a really important conclusion that the planets aren't actually going around the sun in a perfect circle, but they're going around in an ellipse. And that is the fact
the first law of planetary motion. First, let's define what is Kepler's law of planetary motion. Kepler's law of planetary motion are laws describing the motion of the planets in the solar system. There are three laws of planetary motion. Let's talk about them one by one. Kepler's first law of planetary motion, sometimes referred to as the law of ellipses, can be stated as all planets move around the Sun in an elliptical orbit, having the Sun as one of the foci. This means that the planets are orbiting the Sun in a path described as an ellipse. This is the picture of an ellipse. Suppose this ellipse is where the planet Earth moves. The Earth moves along the ellipse around the Sun. The Sun is located at either one of the foci of the ellipse.
The second law, sometimes referred to as the law of equal areas, it describes the speed at which any given planet will move while orbiting the Sun. For example, the planets go around in elliptical orbit, as stated in Kepler's first law, and if you set your watch and measure some amount of the time, let's say a month, the planet will sweep out a certain area and you can calculate what that area is. The second law states that the speed at which any planet moves through space is constantly changing. A planet moves fastest when it's closest to the Sun, and slowest when it's furthest from the Sun. Let us refer to the figure. Since distance 1 is far from the Sun, this has to mean the planet, for example is Earth, is moving slower. The radius got to be relatively long and thin so that the area is going to be equal. Then here at distance 2, Earth moves faster when it's closest to the Sun. But Kepler didn't understand why this was. But the important thing was it showed that there is some kind of relationship here of the planet's orbit around the Sun, and so there must be some mathematical relationship that someone addressed it, and that someone is Newton. The rotation of the Earth on its axis causes day and night. As the Earth rotates, only one half of the Earth faces the Sun at any given time. The half facing the Sun is light or day. The half facing away from the Sun is dark or night. When viewed above the North Pole, the Earth rotates counterclockwise, from west to east. This is also called a prograde rotation. Because of this direction of rotation, we see the Sun rising every day in the east and setting in the west. Because of the tilt of Earth's axis at 23.5 degrees, the amount of daylight varies throughout the year. In addition to rotating on its axis, the Earth also travels along the Sun in a path called an orbit. The motion around the Sun along its orbit is called a revolution. The period for the Earth to revolve around the Sun is 365.24 days or 1 year. The 0.24 days is why every 4 years, February has 29 days. Earth's orbit is not a perfect circle. Instead, Earth's orbit is slightly elliptical in shape, which means that there is one point on the path closest to the Sun called perihelion, and one point that is farthest away from the Sun called aphelion. The Moon's orbit around Earth is elliptical. The point of the orbit closest to Earth is called perigee, while the point farthest from the Earth is known as apogee. Kepler's third law is a formula and sometimes referred to as the law of harmonies. The law states that the squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axes of their orbits. It implies that the period for a planet to orbit the Sun increases rapidly with the radius of its orbit. To better understand the law, let us try to solve the sample problem provided in the module. An unknown planet has an average distance away from the Sun of 3.2 astronomical unit. Let us determine the time needed in years to complete one revolution around the Sun, and determine the value of our third law. Given the formula t squared is equal to kr cubed, where k is equal to 1 year squared over au cubed and r is the average distance, let us plug in the given values. Performing the exponent, radical sign, and manipulating the operation, we'll be having 5.72 years and 0.998 thousandths, or approximately 1 unit, as the time needed to complete one revolution around the Sun and the value of our third law, respectively. In fact, if the same t squared per r cubed ratio is computed for the other planets, it can be found that this ratio is nearly the same for all the planets. Amazingly, every planet has the same t squared per r cubed ratio.
Summarizing up this lesson, Tycho Brahe and Johannes Kepler contributes vastly in the field of astronomy by observing with the naked eye and some highly advanced instruments provided by the government. In this lesson, we have tackled Tycho Brahe and his Tychonic system, Johannes Kepler and his planetary motion. That's all. Thank you for listening. God bless you all.